Okay, so in this video I wanted to talk about the virtual work of member loads, all right, with the PVD. Okay, it takes a little extra consideration, all right? But consider that we have say a beam element in the basic system, and it has some member loads applied. Let's call this W. Transverse loads as a function of X, all right? And then some axial forcing function, WA of X, okay? So the reactions of the basic system, i.e. this force, that force, that force, that force, our 6 local forces, right, can be expressed in terms of the resultants of these loads, all right? A sub A, all right, is the resultant of the axial load function, WA of X. A sub T is the resultant of the transverse load function, and then X bar T is the location of where that resultant acts, all right? So equivalent to this is the statically equivalent system to this is a resultant AA and then a resultant A transverse acting at some distance X bar sub T. Okay, and that's just the first moment function that you learned in statics. Okay. All right. Okay, so then using equation 12, or those resultants there, all right, when we evaluate this term, which we saw in the internal virtual work expression for the PVD, we can just jam out all these terms. All right, we just take the inner product, delta UL1, delta UL2, delta UL6, all right, multiply it by the corresponding entry from P sub L, all right, and we get this expression over here, all right, so negative UL1 times AA. Sorry, I should have drawn the reactions on here, all right. These are the equivalent loads, but then the reactions are going to be A sub A, all right. This one's going to be A sub T X bar T over L, and this one's going to be A sub T 1 minus X bar T over L. Okay, or sorry, it's going to be A sub T X bar T over L minus 1. No, I think I had it right last. Anyway, it's shown up here. All right, that's the reaction. You can work out the algebra. Okay, but this inner product comes out to these 3 contributions at degrees of freedom, local degrees of freedom 1, 2, and 5, and then this reduces to this expression here. All right, we have the virtual local displacement degree of freedom 1 times the resultant axial force, and then this expression times the resultant transverse force, A sub T. Okay? And we recognize that this is just a work term of local virtual displacement times force, all right, as well as a displacement times a force. Okay? So this one is pretty easy to rationalize. This one takes a little bit of inspection to figure out the physical meaning. Okay, and that's what we have in this figure down here. Okay, so this is just looking at the transverse loads. All right. Oops, sorry about that. Okay, we're going to have a resultant force, say A sub T, acting at some distance X bar T, okay? And then the distance that this moves on the chord of the element, all right, initially the chord is here, all right? When we apply virtual displacements, this is going to move up delta UL2, all right? delta beta is the rigid body rotation of the cord, all right? And then this total distance right here, just from geometry, is delta UL2 plus this triangle. All right, delta UL2 is this part, okay? The translation, and then the rotation is going to be the angle delta beta times the distance x bar t. So this total distance right here is given, okay? So the work done is A transpose times the distance that the resultant load moves on the element cord as it goes through its virtual displacements, okay? I know it's kind of a mouthful, a lot to digest, but I think as we get into the examples, it'll make more sense, okay?